Okay, let's start the meeting. I don't think we have any announcements.
Nice.
I don't think so.
Sorry. I don't think we have any announcements. Our speaker today is Pragati Gupta. She is a PhD student in the University of Calgary in Barry Sanders Group. She's visiting UNSW, Andrea Morelos Group right now. She's going to talk about multi-qubit entanglement for clock states for neutral atoms.
Thank you so much, and thanks for this opportunity. So I'm going to talk about generating large-scale entanglement with neutral atoms. And the main motivation behind this talk is that one, this platform is highly scalable, and two, it has the possibility of moving atoms around, which is not so, which allows using parallelization that is not easily possible on several other platforms. So what you see in this picture in the background is basically multiple arrays of atoms, and so this is within a single system, and each single system is divided into these subarrays that have about 9 to about maybe 12-ish atoms in general. And the idea is to have entanglement across these arrays, so not just have entangled states within an array. And the current way to do this is to entangle atoms one at a time, so apply like a bunch of C-naughts to have a circuit-based approach. But having a large depth circuit is really hard. So how can we scale GHZ states to atoms across multiple arrays? And the motivation is that GHZ states are a resource for quantum metrology and quantum error correction. So it would be nice if they can be generated with large ends. So the main problem here is that one, as the size of the CAD state increases, GHZ states or CAD states, as the size increases, decoherence also increases. So as we increase the entanglement, the dephasing rate also increases linearly. So any gain that we get from entanglement goes away with the dephasing. And the main reason why it's impossible to have so generally there's one subarray, and there are many atoms that one can entangle within a single subarray. But the reason one can't go beyond a certain number is that there is imperfect Rydberg blockade. I'll get to what the Rydberg blockade is in a bit, but there's imperfect interaction within a blockade. So you can't have any large number of atoms within a single subarray. So you need to have atoms within multiple subarrays. And on the top of that, even if there are atoms within a subarray, multi-qubit gates are typically very low fidelity gates. So the best gates available at the moment are up to 3 qubits, and so up to 2 qubits, you get something like 99% fidelity. But the moment you get to 3 qubits, these are 97 or 94% fidelities, which becomes really hard to create these maximally entangled states. So a proposal is to create a control scheme such that one can entangle atoms multiple arrays, and to do so within the experimental constraints that are available on the current platforms, and at the same time have some procedures so that we can either detect these imperfections in the multi-qubit gates, or we could have a way that we can sort of post-select on some GHZ states being good. And so the outline for this talk would be, I'd first review the state-of-the-art experiments for CAD state generation, and then a scheme for entangling 2 arrays of atoms, and how that can be done using optimal control, because currently the best gates so far achieved on neutral atoms are using optimal control, but how do you expand that to these multi-qubit systems? And then detecting arrays using something called symmetry protection. And then, so as Abhijit mentioned, I'm visiting the group of Andrea Morelos. So given some time, I would also like to talk about some hardware efficient codes where we are thinking if we can implement a universal set of transversal gates and an extension of the asynchronous theorem, and how that fits into these hardware efficient platforms. Okay, so the state of the art for generating GHZ states is that, so earlier there were some proposal with just like 3 qubits or 4 qubits, and that used to be the breakthroughs. And up till 2020, neutral atoms were sort of the leading platforms with up to 20 qubits entangled within a single array. So, but recently, over the past couple of years, and just this year, there was a paper out on 60 qubit entanglement with superconducting qubits, and so somehow, despite this fact that there's a large scalability of the system, the number of atoms within a GHZ state in the neutral atom platform is up to 20 so far. So, and that atom, so in a neutral atom, there are three levels. There's the clock state levels, which are the 0 and 1. And there's the Rydberg level, which is the R state, which is a highly excited state. So 0 and 1 can think of as the hyperfine levels or just two low-lying levels within an atom. And the R state is something very highly excited. So the R state is what enables this interaction between multiple atoms. So the GHZ state that was created was between the 1 and the R state. The problem with the R state is that it decays extremely quickly. So it has a very short lifetime. So any GHZ states created on 1 and R cannot be used for applications such as metrology or error correction. And this demonstration was done by creating an antiferromagnetic order. What that means is that there's a Rydberg blockade, which means that no two neighboring atoms can have excitation of this atom to the Rydberg level. So, which means that we can alternate between 1 and R. So we create a state which is 1R plus R1, R1. And what we would ideally like is that clock states have lifetimes up to like 200 milliseconds even. So can we create entanglement on these clock states of neutral atoms? And recently there have been several advances that allow this thing to happen, because the high fidelity CZ gate with 99.5% fidelity was demonstrated back in 2019, what they call the living Pickler gate. And that is done using geometric phases. So until now, the gates that were done on neutral atoms were using what they call like an asymmetric series of gates. And this allowed like a symmetric control. So you do a CZ gate with both the atoms seeing the same control. And then this was demonstrated this year up to 9 atoms. So within a single subarray, so within a subarray like this, there are 9 atoms, and you entangle 9 atoms with that single pulse. So why this regime is important is because within a platform, there needs to be a way to control atoms in a scalable way. So if we're controlling each atom singly addressed, the number of pulses and the number of places needed is too high. So generally, global control allows to reduce this overhead. And there was also an approach based on circuits which entangle up to 4 atoms. So our scheme, so the overview of our scheme for entangling multiple arrays is as follows. So we start with a single array in a product state, and then apply, so I'll get to how to entangle these multiple atoms within an array. But say we have a pulse that does that. So we entangle multiple arrays. So we go from plus state to a superposition of the plus and the minus state, and then just shift the basis from the plus to 0. So we have a 0 and 1 state, a Schrödinger cat state living in a single subarray. And then, so there's this possibility to tweeze out arrays tweeze out atoms from a single array. So you tweeze out an atom, and you excite this atom from just being in a superposition of 0 and 1 to a superposition of 0 and R. So now you have some atoms which are, so all of them are entangled, but one of them has this Rydberg excitation and the others don't. So what this allows is that when you put this into another subarray, so this creates an effective Rydberg blockade that so that all of these atoms will either they will see this interaction or they won't. And depending on whether they see the interaction or not, they can get entangled with this red atom. And since the red atom is entangled with this previous array, it creates a two array entanglement. So then apply the same entangling gate that would work for doing a single array entanglement here, apply it here, and then just de-excite it back and have array across across two subarrays. So basically what are we, the missing piece here is that current experimental platforms already have a way to entangle multiple atoms within this subarray. They have a way to tweeze out this atom, but essentially what's happening over here is that there's a fan out gate that from one 0 plus R state, you're creating 0 plus basically 0 plus 1, 1, 1 kind of state. So this fan out gate is extremely hard, one, to get to high fidelities and to even realize in practice, because current proposals are that, so instead of using one excitation to Rydberg level, you excite the Rydberg, the atom multiple times. So you go to multiple higher excitations and then have a series of gates that basically do the C0, but this is not feasible on current platforms. And the other thing is to have an asymmetric blockade, which means that you only apply, so you don't have these global pulses, you kind of apply pulses to a circuit-based approach. So the first, let's think about what the circuit-based approach would be. The circuit-based approach would be, you have this single atom, you apply a C0, you apply a C0, and so on. But on the other hand, there's a way that since the Rydberg interaction is long range, one can have an all-to-all connectivity within a subarray. And so we start with, so this is done using, so generally you drive always on resonance so that you get really fast entangling gates. But if you take a look at what's happening at the slow regime, you get this nonlinear interaction, which is like a squeezing interaction across multiple atoms. And you can create really nice Schrödinger cat states with either 2, 3, or n components. And the interesting aspect here is that, so on the long time scale, you get this JZ square type interaction, which squeezes out the from a product state to an entangled state. And interestingly, so what happens is that so basically if when you have an atom which is in the 0 state and a superposition of the 0 and R state, so the squeezing would only happen when the state is in 0 state and not happen when this atom is in R state, because this effectively is blockaded out. So for all the atoms that see the Rydberg, this red atom in the 0 state, they get squeezed out to cat state. And the ones that don't see this interaction don't squeeze out. So what happens is that you create this superposition where, so the 0 state would be, so the 0 state of this Rydberg atom would be entangled with the cat state, and the 1 state would be entangled with the product state.
Sorry, those spheres that I'm looking at, is that the Wigner function, or is that like?
It's the Q function.
Right.
For a single atom, or what? Like,
So you symmetrize it's the multi-qubit, like you take the n-qubit thing and you go to a decay state basis. And then, so a decay state basis would be, so you take 0, 0, 0, and then 0. So all the symmetric superpositions of having just one atom in the 1 state, and with 2 atoms and so on.
So when I see like a Gaussian blob at like the pole that's looking at me, that's like a decay state where it's all like zeros. Is that right? Or
it's a rotated decay state. So you have all zeros, but you rotate it to the equator or somewhere else. So for example, this would be like a 0 plus 1 all products.
I see. Right. Okay, cool.
And when you see like, so this is up to, for example, 4 components here. So this would, like if this was just 2 components, that would be a superposition of all 0, 1, 0 plus 1
Mhm.
product and a 0 minus 1 product.
Right.
So and so when we look at what the time scale that with the current platforms this would take would be 4 microseconds and independent of the size of the array. So if you can squeeze in more atoms within this subarray, you can basically entangle as many atoms as you squeeze in. And so currently the way current demonstrations have up to 9 atoms for GHZ states, and for just squeeze states, they have up to 27 atoms or so. But we would in this way, what we are thinking is that there would be a laser that shines on this red atom and a laser that shines on this subarray. But is it possible to have one symmetric laser shining on both the single atom and the array, so that you can create entanglement without having this, without imposing this additional requirement on the hardware? So now what if you place?
Sorry, I just have another question. So when you have that Rydberg atom at the top, are you saying that the entire lattice feels the same interaction with that atom, or?
Yes, so if you're close enough, so typically the Rydberg radius, the blockade radius is about 5 micrometers.
Mhm.
So if you have, say, like 9 atoms which are within that Rydberg blockade, then they see the same interaction. So and I agree that that's not what would be really happening. So there would be some that would see this perfect interaction, but there would be a leakage, right? And then I'll get to how one can detect this kind of leakage. So what if you place this atom within that array, and can we entangle this Rydberg atom in red and the other clock state qubits using a single drive? So we start from this initial state, which is the 0 plus IR state with the product state on the rest, and then the goal is to create this. So how this is done is using, again, geometric phase gates. So the idea is that if there's a Rydberg excitation over here, then all of them are blockaded out. But if there's no Rydberg excitation, depending on the number of atoms that are in the one state, you want to add a phase depending on the number. So basically, you go to this basis where you can think of them as a coupled decay ladder. So you have 2 decay ladders, one where there is no Rydberg excitation, where the red atom is in the 0 state, and one where the red atom is in one state, the red state. And then you can write in the symmetrized basis, you can say that the rest of the atoms either have no excitation, which is 0, they have 1 excitation, or up to n excitations. And the coupled part would be that, so since out of these n, 1 is taken, so at best you can have n minus 1 excitations. And you have, and these couplings are between one of this, and so any Rydberg excitation would take the 0, so that it will take 1 atom from this state to the Rydberg state. So why this is, so now you kind of start seeing this Jaynes-Cummings type of interaction in the very large n limit. But in the small n limit, this kind of helps because you have a 2 to power n dimensional system, which is really hard to simulate, and it gets your complexity down to just 2n plus 1. So here's what's happening at the, so there's a ground manifold, which is the one on the left that I showed. And there's the excited manifold, which is the one on the right side over here. And so you want to start from this, and then you want to also end with these same populations, but you want to add a phase to each of these. So you want to add no phases here because you want to keep this as is. And over here, you want to create an entanglement with this one. So you want to add these relative phases here. So now you have a 2n plus 1 size problem. And so there is, in theory, one could say that you can find a pulse that analytically fits, but both current platforms and as well as the optimal way of doing this using optimal control. So what we have made is a new way of doing optimal control. So instead of using a step function with finite size piecewise constant functions, what we do is we first filter it using some smoothing function. So we convolve it with some filter function. And then we calculate exact gradients instead of using an approximate method. So we calculate exact gradients of these pulses. And so essentially, even if you have like a 1 microsecond pulse with some 1 nanosecond precision, so instead of having 1,000 points, you have something like 20 points, but you still have a very smooth pulse because all of them are smoothened out. So instead of having these stepwise, stepwise constant pieces, which would be really bad in experiment, you smoothen it out and you get a really smooth pulse without having to deal with 1,000 parameters and a lot of constraints on your optimizer. So, and so this is done using automatic differentiation. So what this does is it basically gives you almost, so given a particular ansatz, it gives you a deterministic way of creating these high fidelity pulses. And so we checked how the pulse, the scaling, the pulse time varies with the number of atoms. So it increases only linearly. And in contrast, in current experiments, it increases at least quadratically with the size of atoms. And even the best, even the 9-atom system would only take like 0.7 microseconds. In contrast, with the state-of-the-art experimental platforms, it would take, with control techniques, it would take about 2 to 3 microseconds for this pulse. So essentially, what we're doing is from one array, we are going to 2-array entanglement. But since the platform is highly scalable, one can just shuttle all these atoms at the same time and have entanglement across multiple arrays. So you start with just one initial Schrödinger cat state on a 9-atom, and then you scale it to 9 other or 8 other, depending on how you shuttle these atoms. And so from one n square system, you get n to power 2 to power k entanglement in just k steps. So what this does is you don't have a proper fan out gate, but you have so you're relying on the fact that you don't need a fan out gate. You just need to make sure you go from one state to the correct state at the end. So what's the time?
Just how fast it?
So now I'll talk about how to detect the leakage in these gates. So what's happening is that, so you have a Hamiltonian so this is a permutation preserving Hamiltonian where basically you talk about all atoms and they see the same interaction. So then you can go to the collective basis. So instead of writing poly operators in H, you write this collective spin operator. But essentially what happens is that this interaction term is not really the same for all different atoms. So I and J are labels for the atoms. And you see these imperfect control depending on the location of the atom. So we use the Schur-Weil duality. So going from this computational basis, you go to this Schur basis, where if everything was perfect, everything would only live in these diagonal blocks, which are the symmetrized blocks. But if you have leakages, you go to these leakage. And depending on whether this leakage happens due to this or due to this, so if it happens due to this, so if there is imperfect control on a single atom, you only go to the first, so in the Schur-Weil duality, basically you have, so if you have n atoms, you have C2 tensor product C2 n times. And in the Schur-Weil duality, instead, you go to this direct sum of irreps of SU2. So from having 2-qubit, 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 you can go to this basis where you have, say, like an 8-level system, 6-level system, 4-level system, and so on. And there is a multiplicity over here. So for example, here there's this 5-level system. Then there's this 3-level system 3 times and just 1-level system 2 times. So if there's just a single qubit type of error, you would only leak to these. If there's a 2-qubit type of error, you would leak to both this and this. And the larger you go, so depending on where you leak, you know what type of error occurred. And if you can detect this leakage, you can detect whether there was an imperfect control and then fix it. So, and you can talk about these permutation preserving states. So you always stay in this permutationally symmetric basis. And you also, so any leakage detection would basically lead to either imperfect controls or even just decoherence, which is purely local decoherence. So this kind of thing can be exploited with some recent permutationally symmetric codes, where it was shown that even the set of transversal gates is sort of exorted. It's more than the Clifford gate and so on. But that's not what I'll get to. And so the proposal is as follows. So once you have these, once you create these entangled states with highly symmetric controls, use do a Schur transform on a couple of atoms, check whether there's a leakage or not, fix it back, and do this on all of these at the same time so that you can fix any leakages that happened. Okay. So now this is the work that
Sorry, just a quick question about that. So it's clear to me, so that the checking for leakage would amount to measuring which IREP in the Schur decomposition I'm in.
Right.
And I'd be then in one of those blocks you were showing us. How do I map back to presumably the biggest block is the fully symmetric space? How do I map back to that? Because that's not going to be a unitary mapping in general.
So yes, it would be some sort of like a measurement of this, like the syndrome is measurement, like there's a syndrome measurement, but it won't be like, so you would measure in a particular basis, you'd project to the symmetrized basis over here. So you transform from the computational basis to this basis.
Yep, yep.
So then you'll project to one of these IREPs.
Yep.
And then apply a local operation that would bring you back to this IREP.
Oh, so that would actually, you would do something to say one atom that's designed to actually pull you back somewhere into that symmetric space.
Exactly. So
and there is such a, okay, it's not completely obvious to me I can do that, but okay, that's yeah.
So what happens is that any asymmetric control basically brings, so symmetric control, so if I apply a symmetric operation, it would keep the atom within these, so it won't create any more leakages, it would keep the atoms within this IREPs. But if I apply an asymmetric control, it would shift the atoms from, depending on what control you apply, from one of these blocks to this block or this block. So if you know what was the operation that brought you from this block to this block, you can revert it.
Right. Okay.
So now, so this was the work so currently I'm visiting Andrea Morello's group. So what we're interested in doing is some sort of error correction with their system. So what they have is a qubit. So they have a nuclear spin with a high dimensional system. It's an 8-dimensional qubit, and recently they created some Schrödinger cat states on a single nuclear spin. So now can we use that to do some error correction, and in particular some sort of gates? So the interesting thing here is that the Easton-Canal theorem does not apply really to these codes, because the Easton-Canal theorem only talks about transversal gates. But what about the system where you're encoding within a single subsystem? So there's no notion of transversality at the outset. And then there are these covariant codes which say that if you do a universal set of transversal gates, then you can't correct any local error. So can we bridge all of this together? So what we're talking about is a generalization of the Easton-Canal theorem, and whether you can actually do exact error correction as well as do some sort of fault tolerant gates, universal set of fault tolerant gates. And so this picture is just to see that what we mean by universal set is a dense subset of the full logical set. So, okay, so I guess I don't really need to talk about the Easton-Canal theorem here much, but the idea is that if you have a local error correcting code that can correct a subsystem erasure, then any transversal gate would prevent error propagation. But the set of transversal gates cannot be universal. Okay, and then the covariant code construction by Feist and several others as well basically says that if they take erasures at known locations or known subsystems, and then you want to implement a universal transversal gate set, so which means you cannot correct any local error. So you're only relying on the probabilistic fact that an error wouldn't occur. And as you increase the size of the system, so if you have a d-dimensional system, the probability of an error would go as 1 by d squared. So you're only relying on that. So what we now go is to a generalized approach. So instead of taking a poly basis, we take a general graded algebra of errors, what in the operator algebra construction of error correcting codes that was put forward by Cunell, Laflamme, and Viola. And then instead of just relying on whether it's a single subsystem code or multi-subsystem code, you kind of take everything and you allow transversal and non-transversal gates. And why you need non-transversal gates is one, because the idea of transversality is not exactly there for these single subsystem codes, and also in the general system. So what we show is that given a quantum error correcting code, which encodes a k-dimensional state in an n-dimensional physical system, so the set of fault-tolerant gates is universal if and only if the set of errors do not form a properly subalgebra of UN. So what that means is that you need to talk about the algebra that these errors generate and see whether, so basically, if you think about, and the Easton-Cunell theorem sort of boils out as a corollary of this statement, because if you take the encoded weight 1 poly operators, they actually form early subalgebra of the encoded poly operators. So what's happening here is that if your gates are only restricted, so the fact that if you have a Lie subalgebra of the full system, which means your gates are restricted. So over here, your gates do not really generate the full system. So which means they cannot also generate the full logical system. So if this was the physical space, having a Lie subalgebra means that you're restricting yourself to just one of some proper subgroup of this full map, which means that you would also not be able to do a full logical set. So what we then proposed was that, so you have a Schrödinger cat code. So there's a set of universal logical gates that you can do if your Schrödinger cat code can correct quadratic errors as well. So we studied the concatenation of a Schrödinger spin cat code with the W state code. So a W state code is just a decay state code where you have 0. So you encode it. So you encode. So instead of these, so what you see here is that, so you have 0. So ground is the 0 states and the encoded state plus a supposition of where you have the encoding basically. And if you do a transversal gate set, so that would give you, so if you do, exactly. If you give a transfer, if you can do a universal gate over here, you can do a universal gate transversally on this full code. So what that changes is that since you have a universal gate within this Schrödinger cat code, and you can also correct subsystem errors, so it changes the logical error rate from 1 by 2n. D minus 1 to this log d plus 1 factorial kind of scaling. What that means is that you can exactly correct the errors that the Schrödinger cat code can correct, while also implementing a universal set of transversal gates. And this is, so this basically shows the logical error rate versus the physical error rate, where, so for the W state code, basically there's no bound. You have a lower bound on the logical error, just by using the probability of the likelihood of an error occurring. On the other hand, with the Schrödinger cat code, you'll have some place where you can so given a finite distance code, you can correct up to that distance. So which means you can talk about a numerical threshold. So this is realizable on current experimental platforms, one that we are working on with Andre Morello, and the others are superconducting qubits, where again, recently, there was work on demonstrating cat states with superconducting qubits. Okay, so just to summarize, we proposed a parallelized scheme for generating CAD states with exploiting reconfigurability and symmetric control. So also these using these Schur-Weil, so using detection for leakage from the symmetric basis, one can detect leakage in this control, and also hardware efficient tools with universal gates. Yeah.
I have a question. So the control pulse that was there, that you proposed the continuous one instead of the stepwise one. Is that easier to do like a continuous pulse as opposed to like a piecewise one on hardware?
Yes, so in hardware, so for example, if you, so you have to, there's always a loading time of what your control needs to be. So with the continuous pulse, it would always, so there'll be some, say 20 parameters at best. And then there'll be a function that tells you from that 20 parameters how to get this continuous. So you don't need to upload every single data point. On the other hand, if you go to this smaller time step size because you want to do a particular control and because you don't want to have like these very blobs of pulses, so then you would have to have like 1,000 parameters which you upload to that experimental system, which is much slower and also much more inaccurate. So essentially you have a function that links you from that 10 or 20 parameters to the full pulse. So it's much easier in experiment than to generate a function on the go rather than generate a pulse on the go, depending on these fixed amplitudes.
Thanks very much for the talk. I just want to say I'm sorry I was late. I had a meeting I couldn't get out of. I'm tossing up two questions. So at I'm very interested at the end in this thing about universal gates and codes. Just so I understand what the claim, so the basic idea of the claim is that if I've got a setting like a cat code, that it's kind of like it's a bit like a repetition code and it's correcting certain errors. And then you're saying that leaves enough room to get around Eastern Knull and still have some universal gate set for such a thing.
Right.
Is that right? So the threshold you were showing us is against whatever that preferred code is, that error is, like that.
Against a restricted error model.
Right.
So you, for example, just if you have a repetition code with just phase errors.
Yeah.
So you consider just phase errors and you have threshold, like you have a threshold with respect to that phase errors.
Mhm.
If you have bit flip errors, then again, there's no threshold there. So this is still work in progress in the sense like so there's a follow-up of this that you can, if you talk about a peaceable fault tolerance instead of having, so you do some non-transversal gates and then you implement error correction in between. So
Yep.
So you can basically say that this theorems can talk about those non-transversal gates and when those non-transversal gates can be universal as well or not. So
Right. So in peaceable fault tolerance, yes, you're doing non-transversal operations in between instead of transversal.
exactly, but interleaved with error correction to prevent propagation of errors. So you do a non-transversal gate to correct errors, and then you do that so that at the end you don't have too many errors to over the whole thing. But given this thing, so I mean, this is something that I'm working on right now, is that with such a full, allowing both non-transversal and transversal gates and allowing this piecewise fault tolerant set, how do you do a universal gate set?
It's really interesting. So just back to, so the original thing that you're talking about where you have like some like bias noise that's corrected by the Schrödinger cat code. When I perform my transversal, when I perform a gate out of that transversal universal set, does that, can I choose that gate set to preserve the bias? Like, so, oh, wow, okay.
So, and that's precisely because in finite dimensions, you have access to this reference frame which you don't when you have a multi-qubit system. So in entangled system, you would to do any arbitrary entangling phase, you'll have to entangle the system. But for a single system, you get access to a quantum reference frame if you have access to all the frequencies that happen in the system. So that reference frame allows you to do this bias preserving universal gate set that wouldn't be otherwise possible.
And the application you have in mind is still something like Andrea's setting, where it's a large spin
Exactly.
nucleus, for example.
Exactly. So because in their system, they can respect this restricted error model of having only spin-based errors and not the full poly set. So if you have a symmetry on the physical system, which means there are some errors which respect that symmetry. So for example, in this case, that would be just the spin JZ errors or JX errors. So then you can talk about this hardware efficient code. That's why, yeah.
Are there other questions? I have another round of questions, but on a different topic, a more nerdy topic. We do have a few minutes. So I'm always keen on the Schur-Weil duality. And at some point, and it's like literally 23 years ago or something, 20 years ago, I was working on these kind of spin systems and spin squeezing and all this stuff. I suppose my question is, yeah, you're very tightly tying defects in the control. Like, so I'm doing something to one atom or a pair of atoms differently than the ensemble, to then coupling between the blocks of the different symmetry, the different symmetry blocks in Schur-Weil. But it seemed to be the case that you were saying there's some simple way of understanding. If I do something to a particular atom, I can couple particular blocks.
Exactly.
And that's a level of understanding of the Schur-Weil duality that I don't think I've ever had. Like, is that easy to, like, is that written down somewhere exactly how to think about that if I'm going from n qubits to these Schur-Weil basis?
Right. So basically, if you see how you construct these smaller reps, is that so you talk about the Young tableau, which is so the first one would be you have all in the straight line, right?
Yeah.
And then the second one would be one which comes down.
Yes.
Right. So the one that comes down would, in a way, map you to which one you leak to. There's a small subtlety there that, like, I'll talk about it.
Where the one that comes down is sort of the wrong atom somehow.
Exactly.
Yeah.
So the one that comes down is sort of the wrong atom. I'm skipping a few details here, but that was the main intuition here. And the detail I'm skipping is this. So you have n qubits, but the number of these second, like the first leakage, the first smaller set is I think would be n minus 1, which means you can't have all of them leaking out, which means that, and that is because you have so when you label the Young tableau, you always have to label them in the increasing order,
Yes.
like one. So you can't have the one going down, right? So that's why you don't have all the n.
Yeah.
So you can have n minus 1 because you're leaking n minus 1 down, but you can't have n because you can't have the one going down. So which means that when the one leaks, it would be a supposition of all the rest. Like you have a representation there, but it would be a supposition. So you kind of need to be careful on how you're doing the decoding map. But yeah.
I have one more question. I'm sort of aware that probably not everyone knows about Schur-Weil duality, but you know, there's a pointer that it's a fun thing that comes up in lots of places. I just on this thing where you've leaked into a different frame, I can think of each one of those blocks as being, it's an irrep of SU2. So I could make one of those Wigner functions on each one of those blocks. And in some sense, if I've got a large enough number of n, the quantum states on those blocks are somehow the same, at least for certain kinds of leakage processes. So in the context of spin squeezing, I suppose I kind of always had in mind that you could think about the the size of the block as being like the radius of some block sphere or the extent of the polarization of the ensemble.
Exactly.
And you could sort of ignore, like you could do, there are a lot of operations you could do, the operations that are described by these pictures,
Yes.
you could sort of do them without determining how much leakage had occurred.
Exactly.
Um,
Exactly. So anytime you are, sorry for interrupting.
well, I suppose, yeah, go ahead.
So anytime you're doing those kind of attractions, you're kind of staying within them and doing kind of a symmetric interaction on all of them.
Yeah.
Right.
Yeah. And so I suppose what you're saying, I mean, yeah, so what you're saying is that in this more complicated setting, like you might want to do things, if you're not just interested in those symmetric operations, you do actually need to measure to find out which block you're in and potentially correct it. Even though there might be applications where I could just tolerate the leakage.
Yes, so
Over time.
in metrology with squeezing, you can kind of tolerate some leakage because you like in squeeze states, you don't need that much entanglement, like you
Yeah.
don't need but with if you want to create GHZ states, then you need to detect this leakage and kind of fix it.
Right.
But for just metrology, like I wouldn't say that would need all this
Yeah.
correction procedure, but if one was using this for some sort of error correction and stuff, then yes.
Okay. Are there any other questions? If not, let's thank the speaker. Thanks very much for coming. I really appreciate you visiting. Yeah, I don't